We'll start with section 4, chapter 5, the fundamental theorem of calculus. So this is the theorem which connects the differentiation to integration. So here is the statement of the theorem. We have two parts of the theorem. This is the first part, fundamental theorem of calculus. I'm going to identify this as FTC1, the first part of the theorem. So g of x is a function which is the integral of the function f of t. So you integrate some function f and the new function what you get is g. The limits of the integration are a and x. So when f is a continuous function on ab and say x varies between a and b, you are integrating a function f and the answer what you get is g of x. So this g depends on the variable x. When you simplify this integration, your final answer will be g, a function of x. So g is a function of x. And this x you can see in the upper limit here. The upper limit of the integration is x. So if x is a fixed number, then this integral will be a definite number. So if we let x to be a variable, then the integral also varies and defines a function of x denoted by g of x. So let's do this example here. If f is a function whose graph is shown in the figure, the blue lines is the function f, and g of x is integral of this function f, you want to find the function g at several points, 0, 1 all the way up to 5. Then you want to sketch the rough graph of g. So let's do that. Let's write g of x equal to integration 0 to x f of t dt. This is the definition of g of x given in the problem. I also want you to identify the meaning of integration a to b f of x dx. From the previous sections, we know this means it's the area under the curve between the limits a and b. So let's first find this g0 now. Let me write this as g of 0, which means I'm plugging in x equal to 0. So I have the limits 0 to 0 f of t dt. Any function f t integrated between 0 to 0, your answer will be 0. This is one of the properties of definite integral. The next one, g of 1. I'm plugging in x equal to 1. So you have integration 0 to 1 f of t dt. Now you want to identify these points as 0, 1, 2, 3 and these points as 0, 1, 2. Between 0 to 1, you want to see what's the function here for the graph of f. It's a triangle. We all know area of the triangle is half times base times height. Base is 1, height is 2. So I'm going to write this as simplified area, which is 1. G of 1 is 1. Similarly, let me try doing a calculation for g of 2, 0 to 2, f of t dt. From 0 to 2, you have two types of figures here. The first 0 to 1 is a triangle. What about 1 to 2? It's a rectangle. So I'm going to divide this integral as 0 to 1 ft dt, and then I'm going to write this as 1 to 2 ft dt. So 0 to 1 we already calculated on the top, it's integral value 1. 1 to 2 you want to read that as a rectangle. So it's base times height. So the base will be 1 and the height will be 2. So it's 1 times 2. Simplify, you get 3. Similarly, you can calculate G3 0 to 3 ft dt. You split this integral as 0 to 1, 1 to 2 and then 2 to 3. 0 to 1 we know G1 is 1, 1 to 2 G2 is 3, and similarly you want to calculate 2 to 3. 2 to 3 it's a triangle, so the area will be half times base, which is 1, height, which is 2, simplifies to 1. When you sum up, you get this area to be 4. Similarly, calculate the G4, 0 to 4 FTDT will be 1 plus 2, and then you have plus 1, the first three divisions, 0 to 1, 1 to 2, 2 to 3. And then you see area below the x-axis, and it is 2 to 3. Sorry, it is 0 to 4. We want to calculate 3 to 4. So let me shade only till here. This is 3 to 4. And this is 4 to 5. So when you simplify this, area below, you'll have a negative sign. Half times base times height. And this will simplify to 3. Now you want to calculate G at 5, which means it is 0 to 5 f of t dt. So you have 1 plus 2 plus 1 negative 1 from the top until 4, and then you want to add the area 4 to 5, which is still area below the curve, so it's negative 1 half times 1 times 2. Simplify, you have 2. So g of y turns out to be 2. So you were asked to calculate the function g values at 6 coordinates, and we have calculated it. The next one is the fundamental theorem of calculus, part 2. So if you have a function which is continuous on the interval ab, then suppose if g of x is integral of the function f we saw in the part 1 definition, then what suppose we differentiate this function, we get g prime, and when you differentiate the integral sign, all you get is the function f evaluated at the upper limit x. The second part is your FTC2. This is your FTC1, which we already saw. All we are writing is a differentiation format. And this is your FTC2. Integral of a function small f is always the uppercase f. The antiderivative of small f is uppercase f. This is section 4.9. And you evaluate the function at upper limit b and lower limit a. So you have fb minus fa. So let's do this example here. The graph of the function f is given where we take s to be 4 and the function gx is defined by this integral, which is area under the curve, and then you want to answer the following questions. Find the x coordinates of the local max and the min values of the g. So let's do this. First, you want to read this curve carefully, identify the points. S is 4, 2s is 8, 3s is 12, 4s is 16. And I want to mark these lines here. On this interval, you see the function is increasing. And then again on this interval here, you see the function is increasing. And here again, the function is increasing. So 3 times you have an increasing function. And the function given is f, the blue curve is f. So I want you to write the definition what we'll be using now. So let me write g of x in the problem is defined as 0 to x ft dt. We know that integration a to b f of x dx can be written as integration a to b f prime x dx. The reason is small f is equal to f prime. Then integration of f prime is capital F evaluated from a to b. So this is fb minus fa. So we have used the definition that f prime equal to f. So integral of f prime will be small f. Now let's write the definition of so this was the substitution we use. We don't want to write that, it looks so messy. So let me move on to the next one. Let me write g of x is 0 to x ft dt. I can write g prime equal to small f, which means I used ftc1. And I can write g double prime, I'm differentiating again, equal to f prime, which means I did differentiation of this previous step. I get g double prime equal to f prime. So let's move on to this. First part of the question, find the x coordinates of the local max and local min of the function g. So first you want to define g, how the g looks like, and how do you find max and min for the g. If you're talking about the local max and local min of the g, you should see the g prime function changes from positive to negative. Then you can say g prime has a local max at some value, say x. What suppose it changes from negative to positive? Then you can say the g prime has local min. So basically you want to know how the g prime behaves. All you know is the graph of the function f, but you want a definition for g prime to answer this question. So you want to take the part of the theorem which compares the g prime with the function f. So it is our FTC1, the first part of the theorem, which says that g prime and f are equal. So this is the concept we need to do the problem. So whatever happens with the f at some interval will happen with the g prime on the same interval. So now let's go back to the graph and read carefully and list out the local max and the local min. So we have a maximum at 2 and we have a maximum at 10. So which means if I say if we have a max at 2 and 10, the function changes from positive to negative in these points. So here at 2 we have positive to negative change, and then here at 10 again we have a positive to negative change. Similarly, the local min x is 6 and 14. So these are the 2 points where we are seeing the function changes from negative to positive. X equal to 6, x equal to 14. In this direction we have negative to positive, negative to positive. So we have 2 sets of points in each case where the function changes. We have one more point which we want to discuss, x equal to 18. At this point we can say that we have no local max or local min, that's this point 18, no local max or local min, because g prime equal to f is not defined for x greater than 18. You don't know if the function goes like this or if the function goes like this. So that's the reason we say that there will not be able to say anything about the local max or local min for x equal to 18. The next part of the question, where does this g attains its absolute maximum value? So you want to use the definition of absolute max. So here is the definition for absolute max. It's all the GC greater than or equal to Gx. So all the x values for which GC greater than Gx, we call it as the absolute maximum value. So now first let's use this definition, which is the integral definition of the function g, 0 to x ft dt. And we understand that this is the area under the curve ft. So now we start with the first area under the curve 0 to 2 ft dt. We see that 0 to 2 ft dt is the small area here, area under the curve. And then we have this 2 to 6 ft dt, that's this green shaded region. Then we have 6 to 10 ft dt. Then we have 10 to 14 ft dt. Then we have 14 to 18 ft dt. We see the least is 0 to 2, and then as we increase the size of the interval, the area becomes more and more. So we are good to write that the area under the curve 0 to 2 ft dt is bounded below by area under the curve 2 to 6 ft dt. This is bounded below by 6 to 10 ft dt, and then this is bounded below by 10 to 14 ft dt. The last one is the largest area, which is 14 to 18 ft dt. So we know how to calculate this G2, which is 0 to 2 ft dt. Similarly, you want to calculate G10, absolute 0 to 10 ft dt, and then we can calculate G18, 0 to 18 ft dt. And once we calculate these bounds, we see that G2, the smallest area, is bounded below by G10. This is bounded below by G18. So with these comparisons, you will be able to figure out that the value of C, or x equal to 18. So you were asked to find the absolute maximum, and the absolute maximum for the function g occurs at 18. In the next part of the question, you're asked to find the intervals where g is concave upward. So let's do that. When you say g is concave upward, you want to write the definitions which you will be using, which means g double prime is greater than 0. Then you can say that g is concave upward. You also know that gx is integration 0 to x ft dt. And if you want to calculate g prime, you know that g prime equal to f. This is your ftc1. And if you want to calculate g double prime, you do the derivative of the equation 3 on the top. So you have f prime. But what we have to note here is, if you're using this definition, we don't have a graph of f prime. So now let's try to compare and Bring some definitions of this G double prime in comparison of F prime. So let's get back to the problem. Let's write G double prime is greater than 0. Then this implies G is concave upward. So the equation what we want to use in the listed definitions is G double prime equal to F prime. So you will look for all the intervals where the slope F prime is positive. If you read the graph carefully, you see that it's 0, 1, 4, 8 and 12, 16. So the trick here is how do you compare the function f with f prime? That's the trick in this problem. So now you can say that G double prime is greater than 0 on the same intervals 0, 1, 4, 8, 12, 16. Once you say that G double prime is greater than 0 on some interval, you can say that G is concave upward on the same interval 0, 1, 4, 8 and 12, 16. The next example, find the derivative of the function g 3 to 4 t to the 4 dt. In the very first step, you write what you are evaluating. Gx equals 3 to 4 t to the 4 dt. You are asked to find derivative of the function g. So as soon as you derive this function g, all you get is g prime. So write g prime. And you want to derive this side also, the integration symbol. Derivative of the left hand side is very simple, write it as g prime. You also want to derive the right hand side. So when you want to derive an integral sign, you will use this theorem, which is FTC1. Suppose I start with the definition gx equal to 0 to x ft dt. This is the general definition. So if I write g prime x, which means I derive g, I have g prime x, the answer will be f of x, the function f and the upper limit x here. So identify f of t for the problem. F of t is a function of t which is t to the 4. So calculate f of x because the upper limit is x, so it's x to the 4. So go back here, write g prime x is f of x which is x to the 4 and you're done. So it works by comparison. Find the derivative of the function g with these limits. So this time you're seeing the limits as constant -1 all the way up to x. So let me write the very first step. This is your second step. G of x equal to -1 to x e to the t square and then you have a dt. Derive g, you have g prime. You want to derive this integral symbol. The integral symbol can be derived using the FTC. So I'm going to write FTC here, FTC1. This is my step 2. So I'm going to write g prime equals f of x. Identify your f of t, which is e to the t square. So calculate your f of x, e to the x square. So you have g prime x equal to e to the x square. So let's continue with the next problem. Find the derivative of the function g, where g is again defined as an integral. What you want to notice, it's not a simple function x, but rather it is an x square MSE function. So you use a different form of FTC, and here is the FTC you want to use for this problem. Suppose you have g of x equal to integration ax bx, both the limits are functions of x. It might not be a simple function which is just pure linear function x, but it can be x square or x cube. And the lower limit might not be a constant, even it can be a function of x. So when you want to derive such functions, you want to write derivative of function g is g prime. Now when you derive an integral sign, you first evaluate the function at b of x, then differentiate the function b db dx, minus evaluate the function at a f of a of x, differentiate the function dA dx. So now find the derivative of the integral. So first you want to write gx equals integral negative 1 to x square, then e to the t square dt. Now you want to derive this function g, which is g prime, and you want to derive this integral sign. So here is the explanation for derivative of integral sign. Identify the function f of t is e to the t square. Identify a of x, the lower limit -1, b of x, the upper limit x square. So calculate the derivatives of a with respect to x, which is 0, b with respect to x, which is 2x. Calculate the functional value at b of x. It's f of x squared, which is e to the x to the 4th. Similarly, calculate the functional value at e of x, but if you carefully observe, the functional value a is multiplied with the derivative of a of x. But you see the derivative of a of x is 0, so you don't have to calculate functional a of x. So plug all these back in the FTC formula. You have g prime equal to e to the x to the 4 times 2x minus f of a of x, which we did not evaluate because we are multiplying with 0. So it is 2x e to the x to the 4. So you do this FTC if you have the upper limit or the lower limit. It's not a pure function of x, but rather it's like x square, x cube, or any other degree other than 1. Find the derivative of the function. You see the upper limit and the lower limit both are function of x. So we'll again use the new FTC definition which we defined just now. So first let me write step 1, g of x is 2x 3x t square minus 1 t square plus 1, and then you have a dt. So all you want to find is g prime x. So explanation is here. Compare the function, identify ft, t square minus 1 divided by t square plus 1. Identify the lower limit 2x, upper limit 3x. Find the derivative of these functions with respect to x. It is 2 and 3. Then evaluate the function at bx and evaluate the function at ax. So this will be 9x square negative 1 divided by 9x square plus 1, and the top one will be 4x square minus 1, 4x square plus 1. So plug in those here in the formula for g prime. You have 9x square negative 1, 9x square plus 1 times 3 negative 4x square minus 1, 4x square plus 1 times 2. So if the functional value at 2 is 12 and say the f prime is continuous, then you're given an integral f prime value. What is the value of f5? So let's write f prime is small f, then integral a to b f of x dx is integral a to b f prime dx. Integral of f prime is f of x from a to b, and then you have fb minus fa. So let's plug in the values. Integral value is given as 15 2 to 5 f prime x dx. Integral of f prime is the functional value fx from 2 to 5. Evaluate this f at 5 minus f at 2. So f at 2 has been given for u, which is 12. You want to find f at 5. Now this becomes a linear equation with just one unknown, so solve for f5, which is 27. So we did learn a theorem which connects the differentiation to integration, which is the fundamental theorem of calculus. We have two parts, part 1 and part 2, and we have done examples with both the parts here in this section. So whenever you want to differentiate an integral sign, you always have to use this fundamental theorem of calculus. So we'll end this section here.